Vamos apresentar vamos ter a última apresentação da manhã, para em seguida ter o almoço. Agora será estudos de transitórios de manobra de energização do LCA, teste sem defeito. A apresentadora é a professora Maria Cristina Tavares. A professora Maria Cristina Tavares é membro do 3E desde 97 e sênior-membro desde 2008. Graduada em Engenharia Elétrica pela Universidade Federal do Rio de Janeiro, desde 81 e 84, mestre em 91 pela COP, UFRJ, e doutora em 98 pela Unicamp. Trabalhou em empresas de consultoria como a Pitel, Tebas e Promol.
On a test without fault. The presenter is Professor Maria Cristina Tavares. Professor is a member of 3G since 97 and a senior member since 2000. She has a major in electrical engineering by the Federal University of Rio de Janeiro in 1984, a master's in 1991 with COPI, and a PhD in 1998 by Unicamp. She has worked in consulting companies such as Pitel, Temac, and Promon. Since 2008, too, she's a professor at Unicamp and is associated professor in 2008. She works in the research of electromagnetic transients and single pole and triple pole reconnection. Professor, you have 30 minutes. Good morning, everyone. This work has the contribution of all the team members, but especially I would like to highlight the work of Elson, that is currently working at Itai in Taipu. The purpose of the work I've listed here, the motivation is to identify transient overvolters that are going to occur during our half wavelength maneuver. So get the main disturbances that might occur during the test with the purpose of avoid possible damage to the transformer, the generator, and the circuit breaker. The idea is to compare the results from the simulations to the test in the end and identify in advance what would be the mitigation actions. As was said before, I'm going to go faster this because this was mentioned before. Our test is going to be formed with 500 kV lines with similar characteristics. These lines in series are going to form a single line of 2600 kilometers, which corresponds to a little more than half wavelength. Just a little bit of what was saying in the previous presentation. When we're talking about half wavelength, in reality, we say that this is a little more than half wavelength. It's like because exactly half wavelength will be a single point. It's like we have a line in a 0 kilometer, so it is not robust enough in terms of stability as a line that has 190 electrical degrees. This would be around 100 kilometers, so this would be a well-adjusted line. So when we are talking about here half wavelength, we are using this term just to include what already exists in terms of works about this technology, but in reality we're proposing a line of 2600 kilometers in case for the 60 Hertz system. It will be our 190 electrical degrees. So just to adjust things, it's not exactly 180 degrees. This is our circuit. So in reality, to conduct the test, we need to use the north-south interconnections 1 and 2 and enter the northeast-southeast interconnection, almost opening the Brazilian grid. It would be connected by the north-south 1. If I have time in the end, I'm going to give you some basic aspects that I would like to reinforce, but we are really behind schedule. To prepare the test, Camilo has talked about this, but our existing lines are conventional ones, 250 to 250 kilometers with a high level of compensation in derivation and in series, so we need to prepare it for the test. We need to eliminate reactors in deviation, and circuit breakers are locked in the closed position. All the circuit breakers in the remote intermediate substations are going to be locked in the open position because they're going to have an energization maneuver. And the surge arresters that are existent, as was mentioned before, I'm going to show you what is the impact that it has when we leave the surge arresters in the existing substations in terms of the preparation for the test. This would give us a lot of time. If we needed to remove them, we would compromise in terms of conducting a 24-hour test. This would be the amount of time we would use. So what we are proposing is to do a half wavelength in study in 24 hours, 6 hours for preparation, the conduction of a series of tests, and then going back to the system to the original condition. Our lines are similar, but they are not identical. So here I presented the sequence positive and zero sequence parameters. You see that the positive sequence they are very close, and for the zero sequence they are a little bit more distant from each other. Since this is an energization maneuver, our interest is to work at first to the positive sequence. And the first question that arises is, we would like to know how far is valid, or how valid is used to lines that are similar but not identical to represent a trunk, a half wavelength trunk formed by a single line with exactly the same characteristics. So we conducted a lot of sensibility tests with the electrical parameters from the lines inside the test. So we varied not only the electrical parameters but also the lengths, because we have 1,000 kilometers for one line, 1,000 kilometers for another line, and 600 kilometers on a third line. So these are the three lines that are going to form the 2,600 kilometers. So we varied. Instead of working with 1,000, 1,000, and 600, if we play with these lengths a little bit, the goal was to identify how far we can vary them. And if this test was to be repeated in a different part of the world, so we can present parameters. So we thought this was a great contribution. We conducted tests through developed programs, working with 4 poles and also with PSCAD. So in reality, we were varying the impedance for the positive sequence in the line, several lines. And we also varied the lengths. We call L1, L2, and L3 in a way to include the 2,600 kilometers, but varying it so we can identify how far we can use different lines. A little different, how far from each other they could be. Here, we never worked with double circuits because the coupling could have an influence, so we did not check that. Because sometimes it could be easy in a different country to have a long double circuit, and you could assemble a half wavelength there. So we did simulations in time for lines with different lengths, different impedance, different characteristic impedance to around 5%. There is no much difference in results in this case, but when it goes further, for example, we started at 200 ohms and now we had 250, and then we started to have very different results. So with the close characteristic impedance, the main conclusion is that if we use similar electric lines, the link test is going to represent the half-wave line for an energization maneuver. So in this case, we have a small difference of about 5%. This does not compromise the result. Higher values would compromise them. So I cannot go further than 10, 15% of impedance of positive sequence. However, if we had, for example, a length that was very different, if it was short, in our case in 2,600 kilometers, if my case that was very different was shorter than 400 kilometers, there's no impact in the result. This is numbed by the other lengths, so I could have even a higher difference in my impedance. So this information is relevant, I believe, if this test is conducted to validate it. We can use line because lines are too close to each other, but we need to know first how things worked. Another verification we need to make is maintaining the surge arresters in the intermediate substations. Does this compromise or jeopardizes our simulation or not? So here we have a simulation without the surge arresters, only in the ends of the lines for a half wavelength, and surge arresters throughout the line. Here, this is a maneuver without fault, and it absorbs some of the energy, but this does not compromise the result. You can see that the voltages in the terminals are the same. So it's going to absorb some energy here because there's 0.8 or 0.70 something when it starts working. But we can say that keeping the surge arresters throughout the link is not going to compromise it. There is a high importance due to the fact that it allows for the test to be conducted in a short amount of time. So to ask for the system operator to leave these interconnections out, it's completely different than requesting 2-3 days to do the system and also reassembling it. Going to the simulations now, we did simulations in ATP and PSCAD, reinforcing what was said before. If this was a normal study, for example, now Brazil is finalizing a 2300 line in continuous current. All the simulations, all the studies were done using simulators. There's no test. So this will be the largest line in the world for continuous current. The lines in China are a little shorter, and no tests are demanded. Working with simulators is how we do things daily. So due to the length of the line, we are talking about 2,600 kilometers, the transient overvoltages are softened. Disturbances, they hit 2-3 times throughout the line, and they become softer throughout the line. But what we have verified is that the transients are not very high. So we saw overvoltages with no faults. The supportability of lines of 500 kV were not surpassed. Overvoltages that again was way below the limits of supportability of the equipments, and the energization maneuver can be done directly, meaning with no investigation process, because for the halfway length, what is interesting to us is the pre-insertion circuit breaker, and this can be maintained for 20 milliseconds or 8 milliseconds. We varied the number of generating units feeding the system. Initially, we were working with 3, and then we verified that it would be better to work just with 1 generating unit due to the setup of the substation. So we varied the number of generator units, and we also varied with direct energization without any methods, and then the pre-insertion circuit breaker of 400 ohms, which is the existing one, first with 8 milliseconds and then 20 milliseconds. 8 milliseconds because this is the normal procedure, the normal maintenance time for this pre-insertion circuit breaker. 8 milliseconds would be enough time for a 400 kilometers, 300 kilometers line. Some transit times. For halfway length, 1 transit time in our case corresponds to 8 milliseconds for the signal to reach the end of the line. So 16 milliseconds since the first disturbance came to the beginning of the line. I need at least more than that to remove the pre-insertion circuit breaker and have some efficacy. So if the resistor is maintained only for 8 milliseconds, it did not act as a for the wave that is coming back. But to compensate it, on the other hand, we have 20 milliseconds was not what was designed for, so we needed to check the impact of that. So for direct energization, here I present the results of the overvoltages. They are smaller with overvoltages with 3 generator units, so when the short circuit power is lower, the system will have a better response. But with 1 generator unit, we're going to have an overvoltage a little above 1.8. In the transient study, we reached to 1.9 pu, which is not a high disturbance. We are energizing a line with 2,600 kilometers with a single generated with 475 MVA, and the overvoltage I had at the end was 1.90 pu, which would be an overvoltage without. It was an energized at once, so why not use pre-insertion circuit breakers? So it's something that when we start working with half wavelength, we do not expect such a low overvoltage. Here we have the results of our simulation, the statistical result, and we have reached 1.9 pu as an average level, 1.75 pu in the end of the line. Here is at the end of the line. You can notice that throughout the line we have, this will be the highest overvoltages, but in the middle of the line we have 0.75 pu, because in a permanent regime, to sustain the sustained voltage for the half wavelength in the middle of the line is close to zero. It's below, a little above zero, 0.10 pu. So you only have that there's disturbance of the transient that rises this voltage, and then it goes back to a smaller value. So this is how the half wavelength behaves. You can notice here that my overvoltage in the terminal substation, what's interesting in here in the middle of the line, we are going to have a disturbance, and right after we reach our permanent regime. It reaches the permanent regimes very quickly as well. The transient is fast. And here in the middle of the line, my permanent regime, here I have 200 kV in 1,000 kilometers, not exactly in the middle of the line. The surge arresters located on the substations. So here I have this is energy on surge arrestor. I cannot actually read it, but here this would be at the end of the line, the beginning of the line, and the end of the line. So in the end of the line I have 300 kilojoules, which is very low. The capacity is 4.8 megajoules. So the surge arrestor is not actually working. Talking about pre-insertion resistor. Here we have for 8 milliseconds 1.8, and for 20 milliseconds. As I said before, for 8 milliseconds it's almost as I do not have a resistor. It reduced a little. I had 1.9. It was a little bit above 8 in this single case, not a statistic information, but it went down. So I have 84. It went down to 80. It's not effective. Effective would be keeping at 20 milliseconds. Then we have a larger reduction. In the study, it's not yet defined if you're going to maintain the resistor or not, but if it is maintained, it's going to be for 8 milliseconds. I do not know, we still have not defined what the impact of eliminating the resistor. If it's too complicated, we're going to maintain it. What's important for us is to see the energy that this resistor is going to have to consume throughout the maneuver. Here for 8 milliseconds we have 480 kilojoules, and here we reached 1 megajoule. So in reality this needs to be checked. This is not our case. We are not going to maintain for 20 milliseconds, and this value 480 kilojoules is a reasonable value. It's not too high. This part is interesting because we are comparing a half wavelength line with a 133 kilometer line, which would be what we have extra or more than the exact half wavelength. So 180 degrees, these other 10 degrees corresponds to a 133 kilometer line. So we conducted the maneuver in the half wavelength line and on this 133 kilometer lines just to see the disturbances that we would get. In this case, 2,600 kilometers with the surge arrestor installed on the terminal substations, and this one only on the terminal substation. So here the voltage on the sending end, on the short line 1.70 pu, here for 1.60, so the half wavelength is compensating. It should get the same value, but since you damp it more, since the traveling wave goes further, you get smaller overvoltages. This is the short line and our half-wave length line. Here we have our transient is taking longer to disappear. And for the half-wave length, it is damped immediately and it enters into the normal regime. In this case, we have pre-insertion circuit breakers for 20 milliseconds, which would be the proper time for the half-wave length. So in the receiver end, we have a smaller disturbance. In compensation here, we have the energy from the pre-insertion circuit breaker. This would be the voltages in the short line and the half-wave length line using the pre-insertion circuit breaker for 20 milliseconds. So now moving on to the conclusions. The higher the circuit power in the sending end, smaller would be the overvoltages throughout the half-wave length line. We're going to work with a one generator, but this idea is not so strong yet. So the overvoltage is not so severe, even if talking about one generator. In the case of direct energization without any mitigation that are formed by different lines to do the different interconnections, the existing surge arresters in the intermediate substations can be maintained during the test because they are not going to compromise the results. So this was my presentation. Thank you very much. Thank you, Professor Maria Cristina, for your presentation. We are a little behind schedule, but we have at least 10 minutes for some questions. My name is Mauricio Arides from the Federal University of Rio de Janeiro. This is a wonderful work from your R&D. And I was thinking, if we have done everything for this to happen and still not happening, Professor Portela must be waiting for us to do something so this can actually happen. I was thinking about his initial presentation, talking about the issues that we had. And it seems to me that with the need with this interchange between north and south to have two circuits from north and south, it's complicated to convince the national operator. On the other hand, I was remembering, please correct me if I'm wrong, that the three circuits from north-south belongs to a different agent, but one circuit from north-south and the whole of the northeast-southeast, I do not know how is the need for exchange between northeast, southeast. This would be 2,000 kilometers. This belongs to a single agent. Wouldn't there be a different way to complement the 2600? If you remove the whole of northeast, southeast, this is not doable. I believe that the best solution is to work with 1 and 2 north-south. I think finding a time of the year with a low exchange rate. And then we maintain the 3, interconnecting it. With a low exchange, the 3 would be enough to work for a day, a weekend. This does not have any impact. So the reason cannot be this. But you had to go to Bom Jesus. Yes, but the northeast, southeast would be out. You still serve Bom Jesus, which is a load point. And because in Rio das Águas you do not have load. You only have the transformer. You only have a transformer in Bom Jesus where you have a load. Is there a substation? Ibiquara? But then this is covered by the interconnection that comes from Bahia until Bom Jesus da Lapa. We would interrupt in Bom Jesus da Lapa. Or Rio das Águas. No, interrupted in Bom Jesus da Lapa. Bom Jesus da Lapa is part of the circuit. So northeast, southeast from the middle. This would be enough. I really believe that there is a time of the year for us to conduct the test. So we need to sit down. The position of not conducting the test was after a blackout. In 2012, we had just had a blackout, so ONS said there was no way we could do it. But I really believe that we have to sit down together with ANEL to see what is their current position and what can be done, and if they can find a date for us to conduct the test. I'm Vanderlei from ELETRONORTE. I believe, Professor, that with the double circuit lines from Miracema to Gilboese, this Gilboese, Gilboese, Barreira, Bom Jesus da Lapa, Gilboese, São João do Piauí, Barreira, Rio das Éguas, Lusiana. This would be a fourth circuit from the north-south. This would allow for proper conditions right now before Belo Monte, so we can conduct this test. I believe this would be the proper time in 2 years. We are going to continue working until then, right? But I do not know if ANEL, I think ANEL, the National Agency for Energy, and we need to discuss this. We need to escalate the decision a little bit so we can solve this. I think with the conduction of the test, the half wavelength can enter a next bid. And without the test, the impedance is too high. With the test, the impedance is still high, but it's a little smaller.
Thank you for your presentation, Maria Cristina. Francisco Román from Colombia, Universidad Nacional. Yeah, I just want to ask you about the overvoltages you will have. I suppose that you have very long lines. Excuse me, it's the first time I'm talking about this area. But the switching voltages you should be very long and probably almost like a DC waveform. I'm just thinking about the physics of the discharge that you could have on the insulators. I don't know if it should be a problem. Of course, you are very low. The overvoltages are not so low, so high, but I don't know about the physics of the discharge with these very long waveforms. Do you think there is any problem, or the voltages are so low that you won't have any
You are saying that perhaps we could have very long discharge. The time of the discharge should be long. I don't think so. I don't think so. I think it would be just the same as an AC discharge, not a DC discharge. As far, because the wave, the sign we have is AC, so there would be nothing special to have a discharge like a DC discharge.
No, my meaning is when we use for testing switching over voltages, in this case, probably you have longer waveforms in the tail. When you have a switching over voltage. Do you think this is just the point, or you only see AC waveforms?
AC waveform, if I'm not mistaken, I don't think why I should treat anything like special discharge, like the time of the discharge. Should it be different from regular AC discharge, Professor?
Just because of the 500 kilometers line, you have switching over voltages with 250 to 2,000 microseconds length.
Yes.
It's just comparing with this type of waveforms. If in this type of lines you should have something different, something longer, the waveform should be different or not?
I don't think so. I don't think so. I don't know if Professor German can say, but do you expect a discharge that would have longer tails for this, the half wave?
Переходный процесс идет близкий к основной частоте, к промышленной частоте.
I really wouldn't. I wouldn't expect any different behavior as an AC transmission. It should be just the same as a regular AC transmission. Nothing related to the discharge. Okay. Professor.
Yeah, 2 more questions. First one, in the early period, you did say the resistor is something about 220 ohms, is parallel to the circuit breaker. When you do energizing, you use 400. Why?
No.
Why?
Sorry. 220 was the impedance, the characteristic impedance.
Oh, all right.
ZC.
Oh, yeah.
Zeta C.
Yeah, okay. Okay.
This is the pre-session resistor.
Yeah. Another question. When you do energizing, the switching over voltage is 1.9 P per unit. Do you think it's allowed to, it's allowable of this over voltage, or in another way, do you think we need to take special measures to suppress this kind of switching over voltages? For example, in China, for the UHV levels, the switching over voltage is suppressed to 1.6 to 1.7. That's the level. Yeah.
Okay.
Yeah.
In this case, this 1.9 per unit.
So actually, my question is, what's the nominal voltage level you're working on?
Here we are.
500.
Yes, this is the 500.
Maybe that's okay.
Yes.
Yeah, okay.
No, that's because the line is 500 just for the test.
Yeah. Okay. Thank you.
Acho que nós podíamos ir para
A última pergunta, então, pessoal.
Profesor, sou Renzo da Unicamp. Profesor, eu queria perguntar por que comparou a linha de 2.600 com uma linha de 133 quilômetros. Não seria com 100 quilômetros?
Não, o cálculo seria para... Essa aqui seria a linha que corresponderia a um pouco mais de meio comprimento, né? Comprimento exato e um pouco mais. Porque é 190 graus elétricos, aí daria esses 10 graus elétricos, seria 133.
Ah, tá bom.
Não é meia onda, não é 2.500. Meia onda é 2.950, um pouquinho menos.
Ok, gente, agradecemos à professora Cristina pela apresentação. Nós estamos encerrando a primeira parte do seminário, agora pela manhã. Vamos ao almoço.